Hello, everybody. Let us start our discussion on the first module in this course. This is about radiative transfer. In astrophysics, we deal with objects, we try to understand them, and they are very, very far away. The only way we can know about them, at least until recently, was through the electromagnetic radiation. Very recently, we have added another type of radiation to our arsenal. We call it gravitational radiation, which we'll learn about later in the course. But for the most of the humanity and astronomy, it has been only the electromagnetic radiation that reaches to us from the farthest of the universe. And we use it to infer about not only the source from which it is generated, but also about the medium through which it comes to us. How do we do that? Is the question. And part of it will be answered in this first module, where we discuss how the radiation, that is the electromagnetic radiation, gets transferred from the source to us. What are the information it hides inside? Now, when I talk about radiation, there can be many ways, then many different places when one can look at the energy. For example, I can ask the question, say there is an emission at the source that we are talking about. And the source, to start with, let us say that it's like a point like object and a point source, point like source. This is emitting isotropically. Well, that's obviously is a big assumption. But if you think of a star, you are looking at it from very far away. It's not a very bad assumption for most of the stars. There are stars, though, which emits a lot more in particularly two directions compared to the others. But most of the stars are not like that. Now, when such an object will emit radiation isotropically in all direction, it will also emit in different frequency ranges, and it may emit differently in different frequency ranges. It is definite that there is no such object which emits exactly same amount of radiation in all frequency ranges. So what we define is how much energy is emitted per frequency range. So when you talk about range, it is like nu and nu plus some delta nu. Okay. So in that range, how much energy is radiated? So if I ask this question, so the question we are asking is how much energy is radiated isotropically in a given frequency range. You see, still the question is not complete because when I say how much energy is radiated, is it that how much energy is radiated in last 1 hour or in the entire lifetime of the that point like object? So I also need to ask the question in what time interval. So we say that per unit time interval here. One thing we need to understand very early right now is that I cannot ask the question how much energy is radiated at a given time, like 12 hours, 33 minutes, 44 seconds, 20 nanoseconds, 300, 3 microseconds, whatever, exactly specific time. That number is zero. Only you can say within this range of time. So what we do is similarly for the frequency also we cannot ask the question how much is radiated at exactly say 1 into 10 to the 15 hertz. That will come in optical, but that answer will be zero. You can ask how much is radiated in this frequency to that frequency, and then you can modify that to our unit frequency. So you know how much frequency range in which you have calculated the radiation, divide by the range, you get per unit frequency. So instead of any given frequency range, it is better to ask this question or convert this to per unit frequency range, because then I can multiply by what range that I want around that frequency. So if I ask this question, this quantity has a name, we call it luminosity. And because it's given in per unit frequency range, that per unit frequency is in astronomy is noted as specific. Just like when you say specific heat, it is per unit mass. Here it is per unit frequency. So the specific this quantity is called the specific luminosity of the object, and it's written with L suffix nu. So what is L suffix nu? L suffix nu is, let me just for you to remember, let me write. So this is the energy emitted. Remember the emitted part, per unit time, per unit frequency range. So that is my luminosity. That I call the luminosity. Okay. So you see, it's a property of the source. Because we have not talked about transfer of this radiation to anywhere else. It is just how much that the source being able to emit. Right? Now, let us say that we are looking at this source, and so far we have been talking about a point source, right? So let's continue with our discussion with the point source. Say I have the source over here, which is, remember, radiating isotropically in all direction. Now I am trying to observe it from a distance, and this distance I call it S, small s. I denote that distance by small s. Now the question I ask is, what is the energy that I will observe here? So this is the observer. How do I calculate it? Or what is the thing, extra information that I have to bring in here? The observer gets only a part of the radiation. Because the radiation is going everywhere from the source, it only a part that reaches the observer. How much part will reach the observer? Well, if I consider the observer as like a point again, then that number will be zero. I can only ask the question, how much reaches to the observer's say telescope or the eye, which has a finite area, and say that finite area is delta A. If delta A is zero, that's a point, then obviously in that point there is no radiation you can talk about. Just like we said, we need a time range or a frequency range, you also need a range in the area over which you will do the observation. Now we ask the question that how much of the total radiation that is being emitted by the source is sampled by this small area. And that's the easy question to answer, because by the time the radiation has gone a distance s, how much area at which that radiation is spread? Well, you will see that it is spread in a sphere, on the surface of a sphere of radius s. So the total area over which the radiation is spread, and I am assuming that delta is perpendicular to the direction of the propagation of the radiation, so the radiation is falling on the complete face of the area directly. If it is at an angle, so then you have to take the projection along the direction of radiation, but we are not going to those complications right now. So total area over which the radiation is emitted by the source, and what is the property of the source, property of the radiation of the source? Well, luminosity, specific luminosity, right? Emitted by the source of specific luminosity L nu. So what is the total area in which it is spread? Okay, so let us also make it complete. So let's say that at a distance s from the source, what is that number? Well, that number is 4 pi s square, because that's the area of the surface of the sphere of radius s over which this radiation is now right now. So the fractional area, or the fraction of the radiation received by the observer with a detector, let's say, detector of area delta A. So how much fraction of the total radiation it receives? Well, the total radiation is over 4 pi a square, s square, and it gets to test only a part which is delta A by 4 pi s square. So you see now what is important to specify at the observer is rather the radiation received per unit area, because different observers obviously can have different size of their detector, and if that information is not there in the observational number that he quotes, then there will be a problem, because with a different size detector I may get a different number when I'm looking at the same source. Obviously that is not desirable. So you define a quantity which is the radiation falling in the detector, and we consider normally, right? So as you remember that we are considering only the radiation which is falling directly to that area, not in an inclination. Normally per unit area. So that is required to take care of the effect of the different area that different detectors with different observers can have. And as before, it should be per unit time and per unit frequency range, because otherwise again you will land up with the same problem that we discussed before. So this quantity has a name, it's called specific flux. Specific just because of the same reason of per unit frequency range. So that is why the specific word is there. It's written with F, and again suffix new, suffix is for the specific. And just to remind you, this is the radiation falling on the detector. Remember, I write delta E here and I also write delta E here. This delta E is the radiation emitted by the source, and now this delta is the radiation falling on the detector. And this will be, by definition, per unit area of the detector, per unit time, and per unit frequency range. Now, if the source has the luminosity L nu, then this energy delta E is the fraction of that energy that we receive is given over there. So this is delta L nu times delta A by 4 pi a square, because L nu is energy emitted per unit time per unit frequency, and the part of that which is observed, so that is the delta E over here, delta E by delta T delta nu over here, is L nu times delta A 4 pi s square. So we can also write here energy received by the detector. So let me keep this suffix e over here for emitted, because otherwise everything will be confusing. This is the emitted. Sorry, this is the observed. This is delta E times delta A by 4 pi a square. Right? So let me keep things a little bit more organized here. Bring that down. Nice. And so which gives me the flux is related to the luminosity in this particular way. Okay. So all right, that's very nice, but we have to go a little bit further. You see, still we are talking about a single point source in the sky. Obviously, the sky does not have a single point source. If there was a single point source in the sky, I could have always oriented the detected area towards that point source, such that always it is the radiation falls to the area in normal incident. But you can have many point sources in the sky, or even you can have an extended source in the sky. So, like, say, a disk kind of thing, like a galaxy, say, or a planet. So, if I have an extended source in the sky and I have an observer here, say, then in different direction, or if I have more than one sources, then in different direction, the flux coming from different direction can be different. We can only orient the area delta A towards only one direction from which the radiation is coming. From different direction, it can be different. And also, I will like to not know what is the total energy falling in this area. I will like to know how much it is coming from different directions. Otherwise, I will not be able to figure out what is emitting it, right? Either this star or that galaxy or both of them together. What is going on, we will have no clue. So, because of that, we need something more specific than the specific flux. We need something which has that directional information also. Now, before we go into discuss what is that something, let me remind you of one thing here is that, say, I have a meter stick, or yeah, so meter stick in the sky, if you wish. So this has a length, say, smaller, and I'm looking at it at a distance. The distance is d. D is much large compared to L. Okay. So then if I ask you what is that angle that this stick subtends in my point, so if I call that theta, you will say from your knowledge of geometry that is theta is L by D. So this I call the angle subtended by the stick L at a distance d. D is much, much greater than L. And this is in this form, it is in radian, obviously. When I look at an object, extended object in the sky, it's not a stick, it's not a linear thing in the sky, it's rather a two-dimensional object. So if I consider the either end of this object and say, for example, it's a circle, just for understanding purpose, then it constitutes a cone. And how big is the opening of this cone is given by something we called the solid angle. This solid angle is, if I consider the area at the source to be delta A, I write with a different delta here, the small delta. Here I have written with a capital delta. So it's the area at the source, not at the detector. The source area, if it is delta A, and it is if the source is at a distance S, then this solid angle d omega is given by delta A by S square. It's just two lengths, 2 meter sticks if you wish, kept at perpendicular to each other. So then you can see that it will be L square by D square here, L by D into L by D. The same thing is happening there also. So it becomes, the denominator is the distance square here. So this is something that is very important in radio astronomy, in astronomy, sorry. We'll keep it in mind. Now, let us talk about the detection. And we are asking the question, flux turns out to be not a very good quantity to talk about if there is more than one source in the sky, and there are a lot of sources in the sky. So what is that we can now talk about? What we the way the we will be able to figure out or level a radiation coming from a particular source will be the following: the energy observed per unit area, per unit time, per unit frequency. But now I will also say in a given range of solid angle, which means that I have this detector area here, and I am asking the question how much has come to this detected area from that particular solid angle. Okay, so that is, let me draw it again properly. So here, from that particular solid angle. So this direction dependence we have to put in. So let's call that direction unit vector as n cap, and we cannot, again, if we say that how much energy is received from that particular direction, it will always be zero. But we can ask the question how much energy is received from a solid angle d omega or delta omega around that direction. Okay, so that is the question we can ask, and that is what we will try to quantify. Okay, so the question we are asking here, just like we said here, the radiation falling in the detector normally per unit area, per unit time, per unit frequency range. Now we are asking the question radiation, and this area not need to be my detector also, because I can put this area anywhere along the passage of the radiation. So say this is my source and this is my observer. I can put this area anywhere. I mean, I could just call this observer here. The observer actually can be anywhere, right? So I ask the following question: radiation falling in an area delta A per unit time. I'm sorry. So it's not an area delta, it's again per unit area, right? Per unit time, per unit frequency range, and from the direction solid angle, from the solid angle, I'm always forgetting the per unit solid angle. So again, just for the obvious reason, we need to we should talk about per unit solid angle also, just like per unit frequency and per unit time, per unit area, because then if you have a detector which is the solid angle per unit solid angle, it can measure that the solid angle over which it can distinguish between two different directions can be different than the detector that I have. So we call it the resolution of the detector. So depending on that number, the amount of radiation that I receive and the amount of radiation you receive with your detector may be different. But both of us, if we specify in terms of per unit quantities, then that number will agree. So I say towards n cap because that is the direction I want to look at. This quantity is called specific. Specific again for the same reason of per unit frequency range. Specific intensity. It's written with a capital I, and remember that it's a function of the direction you are looking at. So this is the radiation falling. We can write observed, but obviously I can ask this question anywhere in between the passage of radiation. And we will see why I am saying that. And this is also true for the where you observe. So per unit time, per unit area, per unit frequency, and finally per unit solid angle. Okay, so let me observe right over here, just for you not to confuse it with the emitted radiation. Okay, this is the quantity that we will be dealing with mostly, specific intensity, and that is we'll see shortly why that is the case. See, we have been saying I have been saying that the area I can actually choose anywhere in between the source and the observer, and beyond the observer, if there is some observer sitting behind you also. The reason is that it's not only that we want to quantify the radiation that we detect, but you also like to quantify the radiation as it is coming from the source to the observer. Because there can be something happening to the radiation in between, and we want to put those effects in the radiation. It can take out some radiation from the source, and some the medium in between can take out some radiation from the source or add some more radiation to the source. So we need to take care of or take account of how much radiation is getting absorbed or emitted where. So for that, we are devising this quantity we call the specific intensity. This is because this is a quantity which doesn't change between the source and the observer, how much far away the observer may be if there is nothing in between the source and the observer. Like the flux changes, the flux depends on the distance to the observer. But we'll see now that if there is nothing in between the source and the observer, then the specific intensity remains same. How to see that? Well, to see that, we now need a source which is an extended source. So let's call that extended source, like this is my extended source. And let's say that for this extended source, the luminosity per unit area is this. Okay, so this is the total luminosity of the source divided by, say, A is the source area. Okay, so the source has an area A, it's an extended source. Total luminosity is L nu and area is A. Alright, so how much of radiation, so if I consider this to be the unit area in the source, if I am very far away, say here, this is smallest distance away from the source, this is the place where I have kept my detector dA, and I want to ask the question, if I put an area dA over there, then what is the intensity at that position? Okay, so for that, what do we need? We need the total luminosity of the source, how much energy is falling into this area. So how much energy is falling into this area? Well, for every unit area, there is L nu energy being emitted isotropically. You are still considering isotropic radiation. And this is a distance S away I am trying to measure. So just like before, we know that this is the amount of energy falling in dA per unit time per unit frequency range for every unit area in the source. So if I consider the total source, then it will be multiplied by A. So this I get, let us keep count here. So this is dE naught by how much energy coming per unit time per unit frequency range. And if that detector has an area dA, so I divide it by dA, so that will give me per unit area. So if you compare with the intensity definition, what remains for it to be the intensity is the count for what is the solid angle of the source, that substance here. Now, if there is no other source, obviously, the solid angle subtended by the source here, if I call it d omega, we know it is A by S square, right? So if I calculate the intensity now, I have to put in a d omega over here. And d omega is A here and S square here. I'm sorry, I should do the opposite, because then we can see the calculation coming out easily. So let me backtrack a little bit. So what was this? This was dt dA, and I need to calculate per unit d omega. And d omega in the left here, I put d omega is A over A square. D omega in the denominator, so A comes in the denominator, A square goes up. So what do I get as my intensity? My intensity is A times L nu is nothing but the total luminosity of the source divided by S cancels out, A again cancels out, so it is 4 pi. Yeah, so I should have had a dA over here because that is the total energy that I will receive by the area dA. So dA will also cancel out. So this is the intensity that I get, which depends on the luminosity divided by 4 pi. Okay, we have assumed isotropic radiation, but that's all right. But this is the intensity that I get. So what does it tell you? It tells us that it doesn't depend on the distance to the source. The intensity doesn't depend on the distance to the source. And remember, we did not have anything in between the source and the observer, or source and the place where we are trying to measure the intensity. The intensity is something along the direction of the propagation. If there is no emitter or observer which is taking away some of the some of the radiation energy, or giving or adding radiation energy in the same frequency, then the intensity remains the same. So we can safely write that in such case di nu by ds equals 0. And because of that, I nu becomes a very good probe of the radiation, as it doesn't change as it go from the source to the observer. The observer can get the property of the source if they can measure what is I nu. So this is only true when there is no medium between the source and observer. Okay, before we go further, and we need to see the effect of the medium, how you can add radiation to it and subtract radiation to it, and what is the information of that medium that gets imprinted in this intensity, specific intensity. Before we go there, let us define one more quantity which will be very useful for us later. So this is just a definition of one more quantity. We call it radiation energy density. Okay, so how is it defined? It's defined in the following way. So this is again specific because we are talking about only radiation in a frequency range. Radiation in different frequency range hides information of different informations of the source and the intervening medium. So this is the energy present. So I call it P. So if I take a volume, this is the energy present, radiation energy present in that volume, per unit volume, per unit frequency range. If you consider the energy, radiation energy present in that volume coming only from a given direction, then also you have to say per unit solid angle around that direction. Okay. So let us write the definition here. Radiation energy present in a volume from a given direction per unit solid angle and frequency range. Interesting to see will be how it is related to our secrescent quantity specific intensity. So for that I consider a cylinder. Now this is my volume over which I will talk about this specific intensity and u nu. Okay. So say this is the solid angle in which from which the radiation is coming inside this. This the cross section of this is delta A. This is d omega. So I ask the question, how much energy is coming inside this in a given time delta t? How much energy coming in it in our volume in a time delta t from radiation. Now I can label the radiation with its specific intensity. So I say radiation of specific intensity. I knew. Okay. So let's see. Let's ask that question and let's try to answer. So I knew is the specific intensity of that radiation. And you say that it's delta A is the area in which it is entering through. D omega is the solid angle of which I will consider the radiation. I'm not writing d nu because that's always, so we are calculating things per unit frequency. And dt is the time of which I allow, or delta t as we said, I allow the radiation to enter this volume. Okay. Now, delta t is a time interval. So by the time the last bit of radiation enters in that interval, the first bit of radiation would have moved a distance c delta t, and so say that is the length of my length of my cylinder. So on the time delta t, all the radiation that has entered in this volume is inside this cylinder. right? So that volume of that cylinder is delta A into C delta T. Fine. If the radiation density, energy density is U nu inside, so this is U nu n cap. I nu is also a function of n cap, which I have not written explicitly. Then this times the volume and times delta omega, we are talking about the same frequency range, so I'm not writing that explicitly. This should be equals to, this is the energy that has come inside, so this is the energy which is inside. And if you compare these two, you will see that I nu as a function of n cap is C times U nu as a function of n cap. And I can define U nu, which is nothing but U nu for all the radiation coming from all the solid angle. So it's now integrated over the solid angle. This will be 1 by C your I nu n cap integrated over all the solid angle. And I can write it in this way, 4 pi by C, and 1 by 4 pi, I just multiply and divide by 4 pi, that is allowed. This quantity I can call the intensity averaged over all the solid angle. So it's the average intensity or average specific intensity. So what I get is the total U nu, total over all the solid angle, is related to the average specific intensity in this way. In fact, that average specific intensity is the specific intensity if the radiation is isotropic. So I get this nice relation. So let us keep it in the middle. And we'll stop today's discussion there. And let's see what we have learned today. So we started with talking about radiative transfer, and we identified several things. One is what we defined as specific luminosity, which is a property of the source. Then we defined quantity we called flux, which is a property of the observation of the radiation that is being observed, but it depends on the distance to the source, so it is not uh, kind of very useful to use. So then we defined something called the specific intensity, which now doesn't depend on the distance to the source. So if there is no medium in between the source and where you measure the specific intensity remains the same. So we got the first differential equation, di nu ds equals 0. And then we defined something called the radiation energy density, specific radiation energy density, and we saw how it is related to the specific intensity. Okay, so we'll stop here today. Thank you.